In this next section, we're going to look at two special logarithms. We're going to look at common logarithms and the natural logarithms. Common logarithms are assumed to be base 10 and are usually written without the 10 being displayed. And I showed you that last time. On the calculator, it just says log. So anytime you see a log and you don't see a base written, it's assumed to be base 10. So, for example, log 100 is actually log base 10 of 100. And then, of course, this is log form. If we wrote it in exponent form, 100 equals 10 to the y, so y must be 2. And by the way, as long as you're looking at logarithms base 10 and the number you're evaluating is just a 1 and zeros, you can count the zeros to see what the value would be. So 2 zeros, this one was 2. That's only when the number has a 1 followed by zeros. An earthquake of magnitude 4 on the Richter scale versus one that is magnitude 2 is not twice as big, but 100 times larger. That's the whole idea behind logarithms. They're based on powers of 10. Now, the other type of special logarithm we have is called the natural logarithm, and it's based on base e instead of base 10. And actually, instead of writing the whole thing out, we use ln, which is for the natural logarithm. So instead of basically writing it as something that might look like this, in the form we've been using so far, it would actually be written like that. And by the way, you have both of those on your calculator. Here is the log button, again base 10, and note above it again 10 to the x. Here is the natural logarithm, which is log base e. Again, they write it as ln, and then its inverse is e to the x. So, like last time, we have some identities. Ln of e to the x is simply x, because again, ln is really log base e, and so we would have that e and e match up. And then here, ln of e to the x is also just x, because this is, again, log base e of e to the x. So using our power rule, we've moved the x out front. And if we put it into the exponent, it's the same kind of thing. So two very special and very important logarithms that people use. Now, logarithms, of course, can be written with all kinds of different bases. And our calculators, when we want to use them to evaluate expressions, only have log, base 10, or ln, base e. But we can use what's called a change of base property to change some other expression so that it's in something that we could use our calculator to do. And so, for instance, here is the change of base. We have log base a, whatever that number is, of x. And then we've changed it into log base b, and so log base b of x over divided by log base b of a. And the key really is the a went below, the x went above. So as an example, if we have log base 2 of 5, we don't have base 2 on our calculators, but we can change these both into log base 10. Again, no 10 is written, and therefore it's assumed to be base 10. Then using my calculator, log base 5, 0.6990, log base 2, 0.3010. And now that I have these two numbers, go ahead and divide, and I end up with 2.322. So I can use the change of base to figure out other logarithms besides the two that are standard on a calculator. All right, so that's really all that's new in this section, and let's go ahead and do some evaluations. So first off, we have ln e negative 2, and basically since ln e to the x equals x, ln e to the negative 2 has to equal negative 2, because again, ln is log base e, and so here's my two e's that match, and so that's just -2. All right, now sometimes I'm going to have things that are just odd numbers. There's no, write it in an exponent form or something else. We're just going to use our calculator to see what these different things are. So log of 47, 1.6721. Now when I actually do this on my calculator, log of 47, I get 1.672097. Usually 3 or 4 digits is enough. Now if I do log 0.47, I get -0.3279. If I do log of 0.047, I get -1.3279. If I were to do, I'm going to do an in-between here, log of 4.7, that would come out to be 0.6721. So note that the number is bigger than 1. I have the same ending digits, 6721, 6721. If I were to do log of 470, that would come out to be 2.6721. So really all that's happened is I keep adding or subtracting 1 between each one of those. By the way, if I take 0.6721 and subtract 1, then I get -0.3279. So as I kept moving the decimal from 47 to 4.7, I lost the 1, and then to 0.47, subtract 1, and then to 0.047, subtract 1 again. If I go in the other direction, 47 up to 470, add 1. Now, if you're wondering, well, why does it work that way? Well, think for a moment what 47 can be written as. 47 could be written as 4.7 times 10, and so that becomes 4.7 plus log base 10. Well, this is just going to give me a 1. This is going to give me that 0.6721, and so the 47 is 1.6721. On the other hand, if I go to 0.47, well, then that would be looked at as doing log of 4.7 times 1/10, which would be log of 4.7 plus a log of 1/10. But 1/10 is just 1 over 10, which is 10 to the -1. So this whole thing is a -1. So I have my 0.6721 subtract 1, and there I get my 0.3279. So similar digits produce similar answers. Moving the decimal place 1, 2, or 3 just adds or subtracts 1, 2, or 3 to my number. All right, we're going to use some change of bases to find a decimal approximation for these things. So remember that whatever is out here goes on top. So this is going to be log of 27 over log of 9. So the 27 is 1.4313. The log of 9 is 0.9542. Again, I used my calculator and the log button to come up with those. Let's see if we can see that. Log of 27. So you can see the 1.4316. And then when I do the division here at the end, I get approximately 1.5. Now, interestingly, if I were to do this problem a different way, in other words, log base 9, well, 27 is 9 times 3, which means then that this would be log base 9 of 9 plus log base 9 of 3. That is simply a 1. 3 is the square root of 9, or 9 to the 1/2 power, which means then that that's just 1 plus 1/2, or 1.5. Now, if I switch the two numbers around, this time it's log base 27 of 9. So now the log of 9 is above the log of the 27. So the 0.9542 is on top, the 1.4313 is on the bottom, and this one will come out approximately 2/3, which is the reciprocal of 1/2, 1/2 being, of course, 3/2. So note, switching the two numbers is like doing the reciprocal. Now, sometimes the numbers really can't have one go into the other, so we just use our change of base here, log 12 over log 3, which is 1.0792 over 0.4771, which is 2.262. And really, that's all I can do with that one. I can evaluate it, but I can't really do much more than that. And then last one, log of 180 over log of 6. And really, the thing I want to point out here is I can't do 180 divided by 6. It's the log of 180 divided by the log of 6. And when I work this one all the way through, I get 2.898. So, a couple of special logarithms, and using the change of base to allow me to use my calculator to be able to find out what answers are. And in fact, in that last one that I just did, I did the log of 180. I'm going to close it off and then do divide by the log of 6. Please note, it helps to use those parentheses so that I didn't end up with the 80 divided by something else. And then there's my 2.898 as my answer. And that is section 4.4.